12 minus 8. Well, I didn't do that on purpose, by the way. That was cool. So my answer, want to do this for x equals y equals z equals, I'm going to use Maggie's point, 5, -2, 8, and a plus and a plus and a plus, and a t and a t and a t. What goes in front of these t's?
2, 3, 4.
Right there, the coefficients to the t's is your parallel vector. The 2, the 3. Actually, if you want, there's multiple ways to write this answer. You could use any scalar multiple of this, because any scalar multiple of a vector is going to be parallel to that vector. You know, if you're just trying to be silly with me, and multiply a million to all these, and then put it, right?
Their proportional relationship.
That's right. He says the proportional relationship. Cool. Awesome. I'll tell you what, to stay organized, every time you see this problem, I think it is helpful. Use the initial point given, then do this minus this to get your what? Vector, and that will run smoothly when we do chapter 16, the last chapter of this textbook that we cover. We do something called a line integral. And you got to set up your integral, but you'll notice something. It'll be, if you do it that way, these will be your t values. That parameter t. You go, oh, from t equals 0 to t equals 1, because you'll notice when you plug in 0, what point do you get? You get Maggie's point. Guess what happens when you plug in a 1? You will always get what? Check it out. Plug in a 1. You'll always get that next point that's sitting there. Do you follow me? I just think it's a good way to stay organized. It's like, oh yeah, it's like a nice little line segment from 0 to 1. Cool. All right, hey, we'll come back to lines in a second. We've got to talk about planes now. No, there's no parametric equations of a plane, but there's an equation of a plane. Now this is neat one because this is a surface. An equation of a plane. How do we describe an equation of a plane? Now when I make a note, that's a surface, isn't it? Versus a line. Like this tabletop. Alright. How do we do this? What's going to be essential is the dot product of two perpendicular vectors. That's how we're going to form it every time. What's the dot product of two perpendicular vectors? 0. That's how we always form an equation of a line, if you can remember that. We're going to think of the dot product of two vectors. So, I'm going to just draw a picture. Like this. Yeah. Yeah. I'm just going to put this here. Is that plane big enough? I'm just trying to slant it, right? And let's put a vector right here. 90 degrees to the what?
Plane.
To the plane? 5, 2, or excuse me. How about 5, 7, 8 is the normal vector. 5, 7, 8. Perpendicular to a plane. I'm going to pick a point and put it in the plane. Here's the point. The point is 1, 2, 3, like before, just an easy point. And you and I are going to find the equation of this plane.
Equation of what? Which one?
We're going to find the equation of the plane. It occupies that space, excuse me, that point, 1, 2, 3. 1, 2, 3 is in the plane. And a vector that's running perpendicular or orthogonal or normal. I can call this a normal vector to the plane now. It's a normal vector to the point. Here, I'll say u equal n. You're the normal vector to the plane. We have enough information right now to find the equation of plane. So this is critical. We got to know this. In order to get an equation of plane, this is what we're going to need. We're going to need at least one point on the plane. We're going to need that. But then we also need a vector that is perpendicular or orthogonal or normal to the plane. We're going to get the equation of the plane.
The vector doesn't have to like cut through the plane, right?
That's right. It could be anywhere, because can't we slide vectors?
Yeah.
That's I drew it there, and she goes, it could have been over here. But the idea is you can always slide vectors anywhere. You just got to keep the same size and direction. That's the idea. I know I put it right on that plane like that. So very good. Now, here's what we do every time. The other point. We're just going to call it x, y, z. And everyone, what's the dot product of two perpendicular vectors? 0. That's how we're going to form every equation of a plane. So here's the math formula for an equation of a plane. I'm going to do the dot product of this vector and this vector. We go, well, hold up. How do I make a vector out of this? How do I make a vector out of this?
Tip minus tail.
Tip minus tail. So I'm going to do this. I'm going to think of one vector as 5, 7, 8. What's my other vector? X minus a what? 1. Y minus a 2. And z minus a 3. And here's the equation of the plane. Ready? Dot product. 5 times the x minus the 2. Plus, and this is how we do dot products, 7 times the y minus the 2.
Should be X match.
Oh, you're the best. 5 times the x minus the 1. Plus 7 times the, what would be the y component of that vector in the plane? Y minus the 2, right? Make a vector out of that. And then finish out the dot product. 8 times the z minus 3. But too often than not, everyone, that's the answer I get on the test. And I'm cringing. I have to take off points from the student. Let's say the student's name is Fred. I'm like, oh, Fred, oh gosh. It's an equation. Every equation has a what? Equal sign. And do you remember what we said? The dot product of two perpendicular vectors equals what?
0.
So what's here always, no matter what? Equals 0. Equals 0. Equals. There's no t's in here, are there? So I don't want you to confuse this with the line. Although we can pair the twos up and find like intersecting points, and true, we could do that.
This equals 0. Why was that again?
This equals 0 because remember the dot product of two perpendicular vectors.
Oh, it's 0 equals to
And
0.
I think we should draw. What would be that vector right here? Would be the vector what? I'll just put it in here. It would be the x minus the what?
1.
We're calling this a vector sitting in that plane. And the dot product of this vector with that vector has to equal what?
0.
Because it's in the plane. Does everyone agree? That's how we always form it. Now, can you leave answers like this? Absolutely. I have a feeling there one of my the practice set sometimes, I don't know if it's in there, but sometimes they simplify this, so let's do that. What would it be if I distribute everything? 5x minus 5. All right. You might find this easier to deal with. It takes a little extra math. You might want to, I just want to do this. What's all that equal to? See, this isn't probably going to be a 0 now.
You forgot the last.
So I got the 5x, the 7y, and the 8z. Now what I got to do with all that?
Oh,
Oh, good. Add them all together,
Uh-huh.
and I'll put it over here. So do you agree now this isn't going to be a 0 anymore, probably?
Yeah.
Because negative 5 minus 14 is what?
Negative 19.
Negative 19 minus 24.
43. Negative 43. So
Negative 43. And then if I add it to the right side, what's sitting here?
43.
So I don't want to write it like this, but I think this is helpful because most planes are written like this. So you can recognize it. I mean, are there any x squareds? Are there any y squareds?
No.
Any e to the z's? Natural logs of x's? No. No x cubes, x squareds? We're going to get that to that in a second. There you go. What if there's x squareds in the surface equation? Oh, then you get stuff like, did you see meters like this? You can get like things that do like parabolas, but in three-dimensional space. It's going to be like parabolic everywhere. This is just a flat plane, right? This doesn't have to be a 0 once you get it all what? Simplified. Does that make sense? But originally, if you do it this way every time, what's going to be here every time, Mark?
0.
Right, does everyone agree? It's always going to be equal 0. That's the part sometimes I see what on a test. Student, everything right now,
Okay, so 0.
you know, they forgot to write the what?
0.
It's like this is not an equation. It's got to be equal to a 0. Can I check if I did this right? What happens if I put that 1, 2, 3 back in here? This should be a what? True statement?
Yeah.
Everyone agree? I want to make sure I did this problem right. That means this point has to be on this what? That plane.
Right.
So if I plug it back into that equation, it's got to be mathematically true. It's a good idea to check things like that. Now, do you want to find more points on that plane? Sure, you just have to make up 2 numbers and see what the third number is. You know what I mean? Like, everyone, there's a point on this plane. X is equal to 100. Y is equal to 1,000,000. But the value of z, I'd have to do all this math to figure out the value of what?
Z.
Z. There's an infinite amount of points on that plane. But we only needed 1, right? And what else do you need? You always need what kind of vector? That's it. So, and this is the picture just to keep in your notes, to say, boy, if I need a plane, what do I need? I need that thing, and I need a what? A point. That's what I need. If I don't have it, I'm gonna have to find it.
So in two-dimensional, the perpendicular line, the product of the perpendicular line is -1. In 3D, in vectors, the dot product is 0.
There you go. There you go. That was very good. And when he was going back to, remember algebra class, we said, hey, the two vectors, not vectors, but we'll go back to a slope of a line was 2/3. Well, the line perpendicular had a slope of what? -3/2. And he goes, now we're dealing with vectors. The dot product of two perpendicular vectors will always equal what?
0.
0, and how come? Let me write this again. There's the dot product. Doesn't it equal this?
Yep.
What would be the angle if it was 90 degrees?
0.
I mean, what's silly? I go, what would be the angle? If it's cosine of 90 degrees, the cosine of 90 is what?
0.
0, and it just helps us remember that. Good, all right, let's do a tough one. And when I need the equation of a plane. All right, you gotta pick a point.
6, -11, and 4.
All right. Well, I'll pick the next one. 7, 10, 5. I'll pick one more point. How about 9? Actually, this one, I'm going to do -10. I'm going to throw a negative in there too. I'm going to throw a negative in here too. -12. 7. So what I've given you are not vectors. But I'm saying that all three of these points, somewhere in three-dimensional space, have to sit on some invisible plane. You all agree? 3 points determine a plane. There's some plane in space, and they all sit on the plane. My question is, I need you to find the equation of that plane. These are just 3 points. They're sitting on the plane, and you and I are going to find the equation of the plane. All right, what do we need to find the equation of a plane? Let me
The
get this.
parallel line.
Oh, wait, that was for lines, right?
Yep.
For a plane, what do we need? You got it. So I'm gonna put plane. I'll go like this. I'll go like this. I'm telling you, it's all about pictures. This is what we need, don't we? Oh, it looks like I need a point. How many points do I have to choose from? Doesn't matter which point I use, right? Do you all agree? Hey, going back to lines though, Art, you hit some, what about lines? We don't have to do a line this problem. What do we always need? With a line, you needed some vector that ran what?
Parallel. Yep.
Parallel. So when I know it was lines before, you always need a point with the parallel.
Oh,
With a
plane.
plane, you need what kind of vector?
Perpendicular.
Perpendicular vector. A normal vector, orthogonal vector. Okay.
So we create a vector between two of the points, and then
That's where we're starting. That was brilliant. I'm going to get this thing going. He says, why don't we create vectors? I love this. So can we make up letters? Are you okay if I call you P and you Q, and that means you're R? Does that work? So he says, to start with, you're going to have to create vectors from points. That's the first step. So we're going to need how many vectors probably?
2.
2 of them? Maggie, very good. So everyone sound okay if we get PQ? I'm serious. You might be like, can I get RP? Of course. You just need, we got to get started. We got to get some vectors out of this thing. These will be vectors in the plane. So everyone, let me make a note. These vectors we're finding, they're sitting in the plane. Because the points are in the plane. So here's vector PQ. Tip minus tail, right?
1.
1. Crap, here come the negatives. Negative 10.
Then 1.
Thanks for the negative. No, that's good. We like to deal with the negative. Negative 10, subtract negative 11. 1. 5 minus 4.
1.
All right. All right, what's PR? Just to get another vector.
3.
3.
-12. -1.
Yikes. Negative 12, subtract negative 11. That means negative 12 plus 11 stays negative as what?
1.
Is that right?
Yep.
Someone agree?
Yep.
And then 7 minus 4.
3.
But this, I'm still lost. You're going to help me out. Sometimes I draw a picture to get me going. And here's my slanted one. Plane. I got all these vectors in. You know, and we just found how many vectors? But look where they're sitting. You can make errors. These vectors we found are sitting in the what? They're in the plane. And I know I need what? Any ideas? I heard it. Cross product. They said just cross those two. You're going to have this thing all wrapped up. How can I get a vector that runs like that off the plane? Cross them. The cross product of two vectors must be perpendicular to the vector. And you go, what if it goes this way? It doesn't matter. You just need a vector that's what? Normal on a plane. So it doesn't matter if it goes this way or this way. You can do PQ cross PR. You can do PR cross PQ. You can do RQ cross RP. As long as you cross two vectors in that plane, right? So I think I'll do PQ cross PR. All right. And you're good. Wipe it out. 3 minus negative 1. Is that 4? I don't want to rush you, because I know we're doing some mental math here. I know. 3 minus negative 1. That can get nasty though if the numbers are like 26 times 2 minus 8 times 3. So especially on a test, you try to keep them numbers that the student's going to go like this. All right, middle component. Don't forget, start. You got to change the sign when you're done. 3 minus 3, change the sign. Oh, 3 minus 3 is 0. Change to 0. What do you get?
0.
But I do want you to remember that's the one we always change the sign to. And lastly, negative 1 minus 3.
Negative
Negative. Now, do you remember my suggestion of every time I do a cross product? I'm talking 100% of the time. I always make sure I didn't screw this up. Because my eyes are looking all over the place, and I might have drifted, looked at the wrong column. So I make sure that the dot product here is equal to what? 0. And the dot product with this is equal to 0. It's like just a nice insurance. I know I did the problem. There's no way I messed it up, unless I copied a number wrong. And that's true. 4 times 1, 0 times 1, negative 4 times 1 is 0. 4 times 3 plus 0 times negative 1 plus negative 4 times 3 is 0.